So now we're going to talk about the issue of permutations versus combinations. And you may be wondering, why haven't we mentioned permutations yet? It would seem that this would be an important topic in counting. We've gone through all these counting lessons and we haven't even touched the idea of permutations. Well, the funny thing is, we haven't mentioned the word, but the idea is already covered. Any counting problem that you would encounter that involves permutations ideas, you could solve it already with the fundamental counting principle. And in fact, using the fundamental counting principle is almost always a much more efficient way of handling a permutation problem, much better than using the formula. So the funny thing about math on this test, people get formula happy. They think, boy, if I know a formula, then I really understand it. And we really try to discourage that point of view. Memorizing a formula is not the same as mathematical understanding. Understanding a principle, like the fundamental counting principle, that is mathematical understanding. Now, there is one formula I will recommend related to permutations, and this is something that you've already seen in the fundamental counting principle lesson. But if you have n items and you want to find the orders of all n of them, well, that would be n factorial. So, for example, suppose you are putting 5 books on a shelf, and you want to know how many orders can we put these 5 books in. Well, the way you would find this, the shortcut rule, is that would just be 5 factorial. And of course, 5 factorial, we've run into this before. 5 factorial means 5 times 4 times 3 times 2 times 1. If you multiply that out, that's 120. So that would be one shortcut formula you can use. Now, for a more general case, if we have a pool of n items and we select k, and we're going to put those k items selected from the pool of n in different orders, there is floating around out there a permutations formula, a more general permutation formula. If you wanted to, you could go to Google, you could search for it, you could find it. We're going to discourage you from using that formula. And the reason we're going to discourage you from using it is because if you use the fundamental counting principle, you're actually going to have a more efficient solution and you're much less likely to make mistakes. You're actually going to be, on average, much better off not even knowing that permutation formula. So everything I've been saying here is a little bit abstract. Let's talk about a particular problem. How would you solve a particular problem? Here's a classic permutation problem. Now keep in mind, permutation problems, they're not very common. You may see 1, maybe 2 on the test. It may not even show up on the test at all. It is a relatively uncommon scenario, but it could arise. You could get a problem just like this. So let's look at this problem. From a group of 10 committee members, 3 will be randomly selected. 1 is chair, 1 is treasurer, 1 is secretary. These 3 will form the board of the committee. How many different possible boards can be formed? Well, it's clear that order matters here. In other words, picking one person as the chair and then another person as the treasurer, say A is the chair, B is the treasurer, that's going to be different from picking B as the chair and A as the treasurer. So if we swap the order of people around in these particular offices, we'll get a different board. So order matters here. Now, many people would say, well, the way to do this is to use the permutation formula. Again, we're saying use of that permutation formula, we feel, is a longer way to do the problem. That actually makes the problem harder. And the fundamental counting principle is actually a much more sleek and efficient method to use to solve this problem. So what do I mean by this? Well, think about the fundamental counting principle. We have 3 slots: chair, treasurer, secretary. For that first slot, the chairperson, there are 10 people we could pick. If we're picking randomly, any of the 10 could be the chairperson. Once we pick that chairperson, well, then that person's out, but we have 9 people left, and so any of those 9 people could be the treasurer. Once we pick those 2, then there are 2 people out. They've already been assigned. There are 8 unassigned people, and any of those 8 could be the secretary. And if we just multiply those, that gives us the number of boards. So 9 times 8 is 72, times 10 is 720. There are 720 possible boards. And so this is a very sleek and efficient way to solve this problem using the fundamental counting principle, which we've already covered in many videos already. This is much more efficient than using a permutations formula, and that's why we recommend against memorizing that general permutation formula. Now let's back up a bit and look at the bigger picture here. How do you know when you're looking at a problem, do I use permutations, do I use combinations, do I use the fundamental counting principle? And I will say, this is the hardest part about a counting problem, knowing how to set it up, knowing which approach to take. Well, first of all, just keep in mind, the big rule here, the big rule is the fundamental counting principle. Every counting problem on the planet can be solved with the fundamental counting principle. That's why it's called fundamental, because it applies to every single counting problem. So it's something that you can always use. It's more basic, more flexible, and more widely applicable than either permutations or combination. Permutations and combinations are very, very special cases. They're handy shortcuts to have in individual cases, but they only work in those individual cases. They're not widely applicable the way that the fundamental counting principle is widely applicable. That's big idea number one. So if we are picking from a group and there are no repeats and order doesn't matter, so in other words, if I pick ACB or ABC or CBA, all of those count as the same selection, well, then that's a combination, and we use the combination formulas, which we discussed in the previous videos. If we're picking with no repeats, and different orders of the final selection are meaningfully different, and that's what we mean by saying order matters, then it's a permutation, and then we're going to use the fundamental counting principle, which we've already covered in previous videos and which we talked about again in this lesson. Finally, I'll say this issue of order matters versus order doesn't matter. This is actually very tricky. Now, sometimes it'll be very explicit. Sometimes the text of the problem will say the order doesn't matter or the order does matter. Sometimes they'll make it very clear, but sometimes it's not particularly clear, and you need to interpret the problem to figure this out. And it turns out that there's no really quick way, there's no short way to say this. It depends very much. It varies from problem to problem. And part of what's going on here we need to talk about the brain for the second. The left brain, the very analytical, logical brain, that's the side of the brain that is always asking, what's the right thing to do? And many people who are studying for the test, they just want to know, just tell me the right thing to do. Just tell me the right thing to do. That's the left brain question. The right brain question is the question, what is the right way to look at the problem? And if you're asking that question, what is the right way to look at the problem? Well, once you find the right way to look at the problem, what you have to do is perfectly clear. And this is something very important to think about when you're thinking about counting problems. When you read the solutions, don't rush through to what formulas did they use? What do you have to do? What do you have to do to solve this problem? That's the wrong question to ask. The right question to ask with a counting problem is this right brain question. What is the right way to look at the problem? How did they look at the problem? What were the perceptual choices they made in dissecting this problem and setting up, deciding, okay, we're going to count these first, then this, then this. What were those choices? And by studying those choices and learning, you develop the pattern matching skills that will allow you to interpret counting problems more efficiently.